So now, I've given the general overview. I'm going to give the general overview again, and then get into some concrete specifics. I'm going to give you a more general perspective on what you've just heard, kind of interpreting what it means at a higher level. And then I'm going to get into the algebraic nitty-gritty, because I've been told I really have to leave you with some kind of algebra exercise here by the end of the day. So first let me talk about the general thing. My greatest personal interest here lies in developing the kind of mathematics we need in order to understand intelligence in brains or in the natural world. I'm really excited that we can solve crucial problems in aerospace that may be important to the future of humanity, and problems in the intelligent grid. Those are pretty important. But in my view, there's nothing more important than humans learning to use their own intelligence, and that means learning to understand it better. And when we look to what we can build with intelligent systems, if we look out into nature, we don't just see one design for intelligent systems. We see a lot of universal intelligent systems, like the fish brain, like the reptile brain, like the human brain. But they're not all the same. There's a kind of a staircase of growing capability. So as I look at the mathematics of intelligent systems with RLADP, what I see in this mathematics is something like what's on this slide. I picture a kind of a high mountain. A lot of people have imagined that humans are better than other animals because we use language to do symbolic reasoning. And they describe human intelligence as the highest level of intelligence. But when I look at the biology and the mathematics, it just doesn't seem to fit. That's good for the human ego, but it doesn't seem to be real. What I see is a kind of staircase of rising capability. Back when I was getting my PhD thesis, when I wrote my chapters in the Handbook of Intelligent Control, I thought that we could build the most powerful universal learning systems by using some principles I now call vector intelligence. You have a vector inputs, a vector of outputs, and you use methods like GDHP, which assume a vector of inputs and a vector of outputs, and they do the best you can under those assumptions. I have learned that even the mouse brain, the smallest mammal brain, has capabilities far beyond what you can expect, even with learning, even with emergence, in the most general vector intelligence. Crudely speaking, these involve three core capabilities that need to be added to vector intelligence. These are the ability to handle spatial complexity, the ability to handle timescales, and this kind of creativity ability I mentioned. So on the last slide, I talked about the need to use new types of neural networks which can handle spatial complexity. That's one of the three key elements. When you use an MLP, you're down here in vector intelligence. When you use an object network, you're moving up towards spatial complexity. But there's also complexity in time. When you do t plus 1, you're basically doing vector intelligence. But when you have multiple time periods, the way some people want to do in robotics, you really need these new Bellman equations. And right now, people are doing it in a practical, ad hoc way in robotics. But if we want to do it in a unified, intelligent way, we really need these multi-level Bellman equations to structure complicated decisions in time. And then finally, on the very first of my specific slides today, I talked about how we pick actions and how we need brain-like stochastic search to generate options. And that's actually the most advanced of these capabilities. Spatial complexity you can add even in t plus 1. Temporal complexity is a little harder. You don't find temporal complexity without some ability to deal with space. Multi-level robotic intelligence, you pretty much have to be able to see the world before you can really have multi-level task intelligence. And then finally, higher level of creativity really requires that structure. So the greatest challenge to our science in this century is to consolidate vector intelligence, build universal software packages that everybody knows how to use, and add these three elements to the packages to get up to the level of the mouse. And that's still way below the human. Why is the human different from the mouse? I won't talk about that a lot, even though I've spent a lot of time on it. My paper in Neural Networks in 2012, my own paper, talks a lot about what distinguishes human brains and what level of intelligence may be possible beyond the mouse brain, but that's not the core part of this course. So my last general slide. For practical engineering work today, for the coming century, the roadmap for engineering and mathematical work is to perfect vector intelligence, to build packages that can handle spatial complexity. Vogel's chess player was an example of that because he used a simple object net to approximate the value function. The key to his success in chess was using a more complex value function approximator, a simple object net, simplified object net, but that was enough to do masterclass chess, to handle spatial complexity. And this is what we need for things like power grids as whole systems. Vector control can be great for individual generators. There has been breakthrough performance. Vinayagamurthy and Harley, way back in 1994, developed a new DHP controller for turbo generators, which was able to withstand shocks 3 times as big as any other turbo generator controller ever developed. The ability to withstand great nonlinear shocks without losing your generator is really important in electric power. And they could do that with simple vector control in DHP because a generator doesn't involve 1,000 variables. But when you move up to wide area control of the power grid, and there are hundreds of variables, you need the spatial complexity. And the two main things we need to work on here and now is building up and tuning and optimizing this mathematics, and also beginning to develop more capability in this area. The next step beyond this is the multi-level time stuff. I always think of the reptile who can make decisions. And the key to multiple time periods is something like what I call decision blocks. And then finally, at the level of the mouse, is where you start getting this creativity. So now let me finish this lecture by becoming a lot more concrete. In the last lecture, I talked a lot about indirect adaptive control. I showed you this slide. This represents one of the two major ideas in the work of Bob Narendra, who is the #1 guru in North America for adaptive control. His book with Anaswamy is one of the two big classics in adaptive control in modern control theory. I mentioned there's another big classic in adaptive control by Astrom and Wittenmark of Sweden. The book by Astrom and Wittenmark talks about many methods. In some ways it's more complicated than this class. It gives many, many diverse methods. Narendra has focused on two major methods, indirect adaptive control and direct adaptive control. Indirect adaptive control is more powerful and more general, so that's why I'll focus on that. And he's developed it both for the neural net case and the matrix case. And if you want to ask how the method works, for the general nonlinear case with neural networks, it's really all in this flowchart. And you may ask, how do you implement something like what's this in this flowchart? I will give you an example, numerically, so that you can see what it means. But the basic idea is you have two networks. They could be neural networks, or they could be matrices. Narendra and Parasarathi have a classic paper, Narendra and Parasarathi, which is the seminal paper on indirect adaptive control with neural networks. And they have proven important stability results for that case, just as they proved some important stability results for the matrix case, where it's multivariate and linear. But the basic idea is you have one network or matrix that learns to predict the world, and you train it based on prediction error, and you have another network, which I call an action network, but he might call a controller, which actually outputs the actions. So you input the state of the world, you output your actions, and you calculate derivatives. This has stability problems, as I mentioned before. I mentioned a chemical plant that blew up when they tried to use adaptive control, costing billions of dollars, after which people started using robust control, a little more than adaptive control, because they were afraid of it blowing up. People like Narendra figured out ways to tune adaptive control to be more stable, and they proved strong stability theorems, but only when certain very restrictive assumptions are met. And the problem is those restrictive assumptions are often not met, particularly in the complex world of real chemical plants. And that's why a lot of people tend to shy away from adaptive control because of the restricted conditions, because they often do blow up. I remember, for example, with the Miller, Sutton, and Werbos book, there was a test problem on bioreactor control. And several people applied modern adaptive control to that problem, and it just blew up. It was a fairly simple system, but it didn't have the required characteristics. What I said last time was that if you understand this system intuitively, what's going on is that you are making decisions at the present time to minimize error just in the immediate next time period. And that's what I would call myopic decision-making. It's like what Norbert Wiener warned us about, that if you try to move directly towards where you want to go in one time period, you'll often get overshoot, which creates oscillations if you don't look ahead to the future. There are perverse problems out there where the actions that put you closer to equilibrium in one time period create a kind of inertia that puts you further away in the following time period. Kind of an overkill. There are a lot of examples of that. My claim is that adaptive control ought to work better in principle than robust control. It's better to be able to tune your parameters to respond to the needs of the real world, but you have to do it the right way. So the idea of adaptive control is right. It's how you do it with the traditional indirect adaptive control that was the problem. This year, Frank Lewis would probably say something somewhat stronger. Namely, he would say, we have new forms of adaptive control which overcome this problem. And that's basically part of the story. So way back when, in 1972, I proposed a design which is basically the same as indirect adaptive control, except that instead of minimizing square error, we minimize this critic measure of how well you're doing. So the idea is we still have an action network, we're still responding to derivatives exactly like indirect adaptive control, we still have a model network that we adapt to reality, but we have this other network, the critic, the value function approximator, which keeps us stable. Now, is it just boxology? How would you implement something like that? In order to get you started, I'm going to give a linear example. It's not the real world, but it's important to understand the linear case as a stepping stone to understanding nonlinear continuous variables. So what I'm going to do to conclude this lecture is show a few slides on giving you an example of how you would implement indirect adaptive control in the deterministic case, no stochastic noise, in a linear world using what's called least mean squares, LMS adaptation. That's a way of adapting the weights. LMS adaptation was pioneered by Bernie Woodrow in the neural network field, who then popularized it in the world of signal processing, where even today LMS is pretty much the gold standard for most practical work. So this is a very widely used method, very simple. It's so simple it drives people nuts, but the beauty of simplicity is you can implement it in hardware very efficiently. It's a lot better than methods that look theoretically good on paper, but you can never implement them in the real world. And it's remarkably robust if you do it the right way. So I'm going to talk about how to implement indirect adaptive control with LMS. Narendra's work with Parasarathi with neural networks as I recall, is basically using LMS for the neural network case. With matrices, he does a few extra special tricks, but they both work. Now, in order to make this straight, I should warn you that there is another method that Narendra has talked about a lot called direct adaptive control. I won't say much about it because it's less powerful. Indirect adaptive control is the one you really want to think about. And again, Astrom and Wittenmark have many, many methods they discuss in their book. In the linear case, the model of the world is very simple. X at time t plus 1 is a matrix A times x of t plus b times u of t. This is pretty familiar. In fact, you'll see this in linear quadratic Gaussian control. Very standard. This is the linear control equation without noise in this case. In optimal control, linear quadratic Gaussian control, they account for noise all the time. But in normal adaptive control and robust control, they just use it as a kind of a stability margin calculation. But the design is built around a deterministic model where you make believe you know exactly how the world works. And you make believe the world is linear. We assume, of course, x is a vector. It's a bunch of n numbers. And the way we say that mathematically is the vector x is in Rn, vector space of length n. Fancy way of saying you have n state variables. And you have m control variables. And m does not have to equal n. Your controller or action network is linear in this example. Your action u vector is equal to some matrix k times x. And the real challenge in control is to adapt this matrix k. In linear quadratic control, you normally assume you know the matrix A and B, and you design a controller. But in adaptive control, you say, I don't know A and B. I want to build an adaptive system which can learn even though it doesn't know A and B to begin with. So you have to develop approximations for A and B, which I show as A caret and B caret. In the example I'm going to show you today, I'm going to give a simplified example where you're just doing a regulator. And the goal is to make this vector x go to 0. You're trying to tweak your controls to get to the desired point, which is just at the origin for simplicity. In the general case, Narendra talks about making the vector x of t fit some kind of reference model. But in this case, we'll make it unitary. So the way we do it with least mean squares is we do two kinds of adaptation in parallel. In the flowchart, I showed a model block and a controller block. They both adapt in parallel with each other. The model network is adapted so as to minimize prediction error. We define prediction error, E super P, as simply the difference between the actual vector, t plus 1, plus the prediction we would have made using our current approximations from x of t and u of t. And we assume we know all this stuff. We're not talking about partially observed systems in this example. We also concurrently adapt the gain matrix K. It's the action network or the gain matrix, whatever you call it. This matrix K, we adapt that at each time t based on our current knowledge of A and B. And we adapt K so as to minimize the control error. So we have two measures of error we're trying to minimize, prediction error and control error. That's generally defined as the gap between where you are and where you want to be. And in this example, that's just the vector x. So then the question is, okay, we're trying to minimize the two kinds of square errors. At each time period, we adapt the two sets of matrices to reduce square error. How do we do that? What's the mathematics? What's the algorithm? And the algorithm is basically on the next slide. And this is algebra. You really have to look at the slide closely to work out the algebra. I guess this is not something you're going to pick up on the video camera, but I hope you have the slides handy. To begin with, we can use straightforward calculus to work out what is the derivative of prediction error with respect to the estimated weights in our estimate of the A matrix. and you use the calculus. It's the sum of the prediction error for each component times the derivative of that prediction error. And when you work it out, it gets to be minus E super P sub I times X sub J. In other words, the derivative of prediction error in the current time period with respect to any weight, A sub ij, is just the prediction error for I multiplied by the current value at time t of j. And that means, in simple LMS gradient descent learning, the adaptation rule is that in each time period, we update the weight by adding a term equal to that derivative multiplied by some learning rate. And it's an interesting question. What should that learning rate be? That's a general issue for any gradient descent method. It's true for classical nonlinear optimization and operations research. It's true in neural networks. It's sort of a universal challenge how to pick the learning rate, but there's a lot of mathematics that's been developed for that. I should add that this is one case where Narendra does something different in the linear case. In the linear case, there's something called recursive least squares, which avoids the need to have a learning rate. It can be very convenient, but it's a lot more expensive. All of a sudden, you're not in the realm of computational cost O of n to the squared. It's more like O of n to the fourth. It's a little easier to have adaptive learning rates. Make this work, and you do the same thing with B. So basically what I've shown you here, these are the algorithms for adapting the A matrix and the B matrix so that they can become a better and better model of reality. And those things work. But what about the controller? And you may remember in the flow chart, I showed some arrows. This will be where you want to cut. Okay. On the slide, I showed some arrows representing the flow of derivative calculations back from control error to the controller. And the arrows went through the model network. And what that means is that the weights in the controller change the controls, which change the outcome through the model. And you have to account for that causal flow if you want to know the impact of your control weights on the error. Those derivatives depend on the model. And if you work out the calculus, you can see that. The calculus is a little more complicated precisely because that's the physical reality. So this is a derivation you got to look at closely, but it's really pretty straightforward. The derivative of control error with respect to a control weight or gain, k sub ij, is the sum over k of the control error for k. And this is the error. The error is the value of x in this simple example, times the derivative of the control error with respect to the weight kij. But then we have to ask, what is that derivative? Well, we know what x sub k of t plus 1 is if we believe the model. It's just simply a term that's a times x. That's not influenced by controller, so the derivative of that with respect to kij will be 0. But then there is another term, which is b times the controls. And we need to think, how does the weight kij affect the controls? Now, the weight kij only affects the controls in the case where alpha is I. The weight kij doesn't affect the u sub alpha for an alpha that's different from I. It only affects u sub I. So this thing simplifies. We only need to think about the case where alpha is I. So what it reduces to is the sum over x sub k b hat sub ki times the derivative of ui with respect to this weight. And you'll notice ui is also a linear sum. This derivative is either 0 when j is different from beta, or 1. So the whole formula is relatively simple. After you work out the calculus, it's a lot more complicated than this guy up here. You still have to propagate through this matrix B. But at the end of the day, it's relatively simple. You're propagating through the matrix B, you get this formula, and at each time period, you adapt the gain, Kij, in proportional to this guy. And let me point out that in the general nonlinear case, we still need these derivatives, and it's more complicated. But in the general nonlinear case, there's a tool I want to talk about in a later lecture. I showed you the equation, the chain rule for ordered derivatives. Some people call it backpropagation, but it's much more general than what most people seem to know about. The chain rule for ordered derivatives gives us a universal method to calculate all the derivatives we need for this kind of nonlinear system accurately in a single quick pass through any nonlinear differentiable system. So we don't really need to work this out by hand if we implement software that implements backpropagation, which we can apply to any nonlinear differentiable model. But that's for later. Right now I want to talk about the linear case. So this is how to do it. The question is, does it work? It turns out indirect adaptive control works just fine, really in the general case, if n equals m equals 1. And half of the book by Narendra and Anaswamy talks about that case. It also can be proven to work under very special circumstances for larger n and m. But if you look at those theorems, they're pretty tough to understand. And at the end of the day, you realize they are very, very special circumstances. They are not what generally holds. The conditions are not obvious. People have tried to play games with things called chattering and multiple models to overcome the problems that exist in practice, but it doesn't work as well. And the question is why? Why doesn't adaptive control work better than robust control most of the time? Why can't we make it work better? Exploiting the ability to adapt should always be an asset. Why does it seem to be a liability? It's not the learning rates. Narendra and Anaswamy studied how to control the learning rates so that you don't overshoot in the learning, which is a big worry. If the learning rates are small enough, you have error in the beginning, but if your starting controller was good, the error shouldn't be too expensive. You learn more slowly than you'd like, but slow learning is better than nothing, and you can guarantee stability on the learning side. And with slow enough learning, your estimates of A and B will always approach their true values, so that's not the problem. The problem lies in how do you pick the controller when A and B are known. The problem is if you pick actions that are myopic, that maximize or minimize control error in the next time period without considering the further future, you can overshoot and be unstable. And that's basically what I was saying before. So as an example, considering what happens in the next more complicated system. Suppose n is 2, but m is 1. You only have 1 degree of control, but there are 2 variables in your system. So we have a linear system defined by a 2 by 2 matrix, 4 numbers, and B is a 2 by 1 matrix, 2 numbers. And I would like to leave you with a challenge to think about. It requires a lot of creative thinking, and I hope that over this week you'll try it, because it's really useful to do this kind of thinking. The challenge is, you should be able to come up with a numerical example of A and B, that's 6 numbers, where this control goes unstable. And let me give you a hint, because it's not entirely trivial. The hint is, you can use geometry to work out what the K is that minimizes control error in the next time period. Use geometry to work out what K is, and then use your knowledge of eigenvalues in matrices to evaluate stability. And if you can't figure it out, I'll describe it in the next lecture, but this is the challenge. So in the next lecture, I'm going to talk about stability analysis for linear systems. I'll talk about how HDP and BAC solves the problem, how to implement them in a simple way Simple but powerful enough to solve the stability problem. And that gives us the first method of adaptive control for the linear case, which is stable without strong assumptions and which is only as expensive as order of n squared computation. And Astrom and Whitmark have adaptive control methods which are stable with much more computational complexity. I believe this is the first time anyone came up with stability for linear adaptive control so general with only O of n squared. But that's for next time. Thank you.